Thank you so much, Professor Guo Jun Hong and Mr. Ari Priharta. It's a very interesting and engaging discussion and presentation. Ladies and gentlemen, next we're going to have a presentation by Professor Dr. Markus Diantoro, the next keynote speaker. He will present a paper on supercapacitor and battery. And we'd also invite Associate Professor Nandang Mufti as the moderator. Before that, I have one short pantun right here. Let me just read it for you. 1, 2, 3, 5, 6, 7. Together, let's see Markus' presentation. Mr. Nandang, over to you.
Okay. Good morning, ladies and gentlemen. Okay. Assalamualaikum warahmatullahi wabarakatuh. How are you, Prof. Markus Diantoro? Okay. Are you ready?
Sure.
Okay.
Thank you.
Thank you to the host. First of all, I would like to introduce myself. My name is Nandang Mufti. I'm head of a Center of Advanced Material for Renewable Energy. And in this morning, I'm responsible to take care about this session. It's a great pleasure for me to introduce our keynote speaker today, Professor Markus Diantoro. He is head of the Institute Research and Community Service, State University of Malang. Not only that one, he is also a very good scientist and also entrepreneur. In this morning, Professor Markus Diantoro will talk about supercapacitor and a battery. Yeah, this topic is very fascinating, both from the scientific aspect and its application. Okay. Before we proceed with the presentation for our keynote speakers, let's watch his curriculum video. Okay, please. Okay, thank you. Professor Markus Diantoro, you have 30 minutes to giving a sharing about your presentation and maybe around 5 or 10 minutes for the discussion. Now it's time is yours.
Okay,
thank you.
Thank you, Dr. Nandang. May I share my screen with my own? Hello, Pak Nandang, can you hear my voice?
Yes.
Okay, thank you very much. Okay, let me start. Thank you for the great occasion and opportunity to be here in the second I-CoRE International Conference on Renewable Energy. It looks this is a very great conference starting from yesterday. I followed for this today's conference. I think this is quite a distinguished conference. Thank you and congratulations to the chairmen and all of the committee. Thank you for giving me the opportunity to be here to share my thoughts, experience, maybe skill and some knowledge and also to give us feedback what we have done. Although on this data, what we have presented here is not the newest one. You can see and you can follow on the other articles that maybe already presented yesterday and also for today's conference. Okay, thank you, Pak Nadang, and all the committees, distinguished guests, all the experts, and all of the participants. Thank you also to the Rector of Universitas Negeri Malang, Professor Dr. Ahmad Rofiuddin. Okay, let's move to next slide. I think this is a short outline. It's not all maybe discussed, maybe just skip it. Depends on the time. Okay, firstly, I would like to show you. These are two cars from Tesla. Maybe you know that Elon Musk now will as a billionaire. A week is about 8 trillion is incentive. So maybe the energy storage. Sometimes people also asking which one is important, which one will be used, is the battery or supercapacitors. Okay, before we are going to the questions, maybe let me show you two regulation from our ministry, number 44/2020 and number 44 and 45 2020. So these two regulations of our Ministry of Indonesia is regulate and promote to produce and use cars or maybe any other type of electric, based on electric motors. So that's why this is already open for us that Indonesia also follow the international regulation. As we have seen that in Europe, on starting from maybe already 5 years ago, they would reduce from the gasoline. They will use totally 100% of electric cars. So Indonesia also follow that rules. Maybe Indonesia quite late, but this is okay. It's now ready for us. Will you take part on this scientific, or maybe you will take part on industrial part of energy storage? Okay, talking about the cars, electric cars, maybe the most important one is battery. But you don't know that Tesla is also already used, part of the battery is a supercapacitor. So it means when you, what you need, when you need a longer distance, of course, you need a very, very high energy density. But if you need to high climb, so you need to high acceleration, so the battery is not suitable for that implementation. So you need for high acceleration, you need a capacitor. Okay, many kind of questions will arrive. So when we take a look on the structures of the composition of the cars, maybe half of its weights, you can see here, is almost a battery or energy storage. So you want or do not want, in next future, all of the energy storage will take part of your life. This is not question. This is not an option. The energy storage will introduce in our daily life. So we should ready. I think it's not only for to be a user. You or we should take part in the producing, transportation, or maybe trading, or any other in industrial of energy storage. Okay, talking about energy storage, actually there are many kinds, many types of energy storage. Based on the electrical, mechanical, thermal, electrochemical, and maybe chemical. This is for pure chemical. Maybe we know about the fuel cell, electrochemical, battery, and hydrogen. For thermal, we know heat storage. Mechanical, you can use a hydro pump, flywheel, and compressed air. And the electrical, maybe the most of physical, yeah, capacitor, maybe supercapacitor, and also could be superconducting magnetic energy storage. Okay, maybe it's good for us for take also for the superconductor, but we know that for superconducting superconductors is quite high price. It's not simple one, but we could take part on that. Okay, firstly, let me not show you, but let me remind again, refresh again for what is the mechanism, basic mechanism on the battery as well as supercapacitor. From this one, normally and the pure of the capacitor or supercapacitor is electrical or physical, but for battery is actually chemical or electrochemical. So that's why maybe we could not clearly decided which one is actually battery, which one is actually supercapacitor. But on the structure is almost the same. We have cathode, anode, and then also separators here, and this is ion. This for load. It's also similar happen from the supercapacitor, but of course supercapacitor or ultracapacitor is mainly based on the capacitive one. So it depends on the active materials here. The original of the supercapacitor is the physical. Physical means this active materials based on the dielectric one. But of course, without any dielectric, without any separators, we still have a capacitor, but not supercapacitor. So when we can manage of the structure of the supercapacitor separated by separators from this right side, so there should be a combination between the electric or physical properties of physical mechanism and some also a combination between this capacitor or supercapacitor with this battery. So that's why, as I have said previously, Tesla now make this combination. The combination maybe appears into two different types. One is the combination between two different devices, or maybe can be appears in one device. Okay, we will see later. Okay, let's give back to the history of development of capacitor to supercapacitor. Around 1746, from Leyden jar, as we have previously mentioned, that the capacitor is mainly structured from manufactured from two plates of conductors. In between of the plates could be vacuum, air, or any other dielectric materials. So from this year to this year is still physical. But still start from 1971, now the electrolytic capacitors also exist till today. But till today, for the capacitors, still very, very low capacitor. But of course, it depends on to what kind of usage the type of capacitor we will use or implement it. So next 20 years from this era, so the modification on these active materials, the modification of the substrates or volta cells, volta series, and also to make the very thin and small particles could enhance the energy density, specific capacitance, as well as the power density. So on 1992, there is a group of scientific in the Europe. They produced an asymmetric and hybrid capacitors. So till 1971 is a mostly symmetric capacitor and very low specific capacity, also energy density as well as power density. So start from this to this existing years where we are now. We are now having many kinds of capacitor, or we as the capacitor have very high energy density and high specific capacitance compared to our previous era, so we call it super or ultra capacitors. Okay, maybe we can see what is the difference from the form of dimension. Maybe we could not divide it, we cannot determine which one is actually capacitor, supercapacitor, or battery. But from the mechanism as well as from its performance, so we can decide it. Which one we can determine which one is supercapacitor, capacitor, or battery. So for giving us a picture, these are physical or electrochemical parameters, and these three types of electrochemical energy storage. Yeah, this is a battery, capacitors, and this is a supercapacitor. So simply, actually, we can determine which one is battery, supercapacitor, or electrostatic capacitor. So from the charging time, the battery could be take 1 to 5 hours, as we have seen in our laptop or maybe in our cell phones or mobile phone. For the electric capacitor, we found around microseconds, supercapacitor around seconds or half of seconds. So for discharging also similar, yeah, but for battery around half to 3 hours, electrostatic is similar, and supercapacitor also similar from the charging time. The energy density, so this is could be one of the most important parameters. We can decide it which one is the battery, electrostatic capacitor, or capacitor. That is energy density and specific power density. So for battery around 10 to 100 watt-hour per kilogram, and electrostatic around milliwatt-hour kilogram, and supercapacitor reach to 10 watt-hour per kilogram. But the specific power, supercapacitor is the king, 2000 watt per kilogram, and specific power for the battery can reach only 50 to 200. Of course, electric capacitor, due to the very short time of charge on the discharge, we can use this at very short time with high energy, so we call it specific power. Of course, we can read in detail in next occasion, because we have many slides. Okay, maybe we can have a look on the Ragon plots. This is energy density or specific energy, what hour per kilogram. Here at the vertical axis is specific power watt per kilogram. So we can have a look here, the fuel cell and battery somewhere here, very high energy density, but for the supercapacitor is very high power density, but much lower the specific energy density. But people already try to find modification to composite between these supercapacitors as well as the battery. So we know that nowadays we have new term, what we call supercapacitor. Means the mechanism is as physical as well as electrochemical. So this should be asymmetric, not like as EDS supercapacitor. So we call it supercapacitor. So in between of the supercapacitors and the specific energy density can reach in a similar way, similar scale of the battery. So now people going to pace away to run the result of this supercapacitor. Okay, we would like to show you shortly what is the structure of supercapacitors. The supercapacitor, this also happen on battery, can be constructed in two different electrodes. This is the electrode 1, this is electrode 2, with the active material here and separated with the supercapacitors. And we can make a series to many sheets of this sheet of the electrode of the supercapacitors. Okay, we should run out. Okay, here is the supercapacitor when we divide it in the components. Of course, the first one is the component of the electrolyte, could be organic from polymers, also possible, aqueous one, and the ionic. And nowadays, people also use the solid state electrolytes. Yeah, we have tried also to use solid state electrolytes. Depends on its material, supercapacitor can be divided into two. Actually, only EDLC and active materials. Active materials based on pseudocapacitance, we can have seen on that the materials of supercapacitors made of metal oxide and conducting polymers, or maybe a combination between them. And for the ADLC, this should be a symmetric one, means the right side or the top and the bottom part of the electrodes is the same. So we call it a symmetric one, separated with the separators. So according to the ADLC, we have three kinds, heterohedral carbons, planar carbons, and exohedral carbons. We got CNT and CNF. For the planar, we have graphene. For endohedral carbon, we have activated carbon, or any kind of any other kind of form of activated carbons. So according to activated, we can have seen on the next slides. But up to now, people also made of materials of supercapacitor a combination between EDLC and active materials. We call it composites. Yeah. So based on this material, actually mostly people use EDLC and active material, but sometimes and nowadays we have seen many kind of supercapacitors made of composites. For the configurations, we have actually two types. The first one is symmetric one, means the bottom and the counter electrode is the same. So we call it symmetric and separated with the separators. And the other one is asymmetric, means the counter and the base electrode is not the same. but the mechanism is the same. So we call it asymmetric only. But if we use asymmetric with different mechanisms, so we have two types. Yeah, two types. This one, battery types and pseudo capacitive type. The battery type, this one, what we call it this as supercap batteries, as we have previously mentioned. Okay, here we are, carbon-based supercapacitor and its performance. The performance of the energy density, this is specific surface area here, and the density gram per centimeter square. This is the performance, yeah, farad per gram, the energy, no, sorry, this is not energy, this is a specific capacitance, yeah, based on the organic, depend on its organic aqueous or organic electrolyte. So even we have the same carbon materials or composite one, the electrolyte is also made their performance difference. Okay. It looks time is run fastly. Yeah, maybe you have seen this.
5 minutes, yeah, around.
Oh, only 5? We need 50, Pak Nadan. Okay, I will run.
Yeah,
Thank you, Pak Nadan. I will run it.
Okay.
This is only the first introduction. Okay, shortly, in more quite detail, the component of supercapacitor can be we have previously mentioned, but the electrodes sometimes we need another kind of material. We call it binder. This is the active materials. This is a binder, and this is conductive materials and substrates. Nowadays, substrates also very, very important, not only as a metal, but they have good conducting as well as adhesive between the conductive substrate to the active material. So that's why we need to make this active material to be attached strongly. And why? Because the electrodes or maybe ions should be flow to this conductive substrates. When it's not so strong, so will be heat appear here, no energy flowing here. Okay. The electrode supercapacitor, maybe we can see the conductive materials and active materials and binder. So how to choose? It depends on you what kind of specific surface area and specific capacitance with how high price you will choose. Because now we are not only talking about the scientific, but we now should talk about also the cost, because we need to use this for the any other kind of energy storage in our daily life. So maybe you can produce, you can sell it, you can promote compared to the other kind of supercapacitor or batteries. Okay, I will skip this one shortly. We have 4 types of carbon materials: 0D, 1D, 2D, and 3D carbon. Okay, this is the allotropic form of the carbons, many kinds of hexagonal graphite, fluorines. This is the promoter of Pak Nandan, the Prof. Thomas Paltra, so find this fluorines around 20 years ago. And the derivation could be carbon nanotube and so to carbon fibers. Well, we have used for today's activities for the activated carbon for supercapacitors. The activation of the carbon could be used in two ways. First one, physical activation, mainly use of the thermal, and the chemical activation, mainly use chemical reaction. So, but for nowadays, people can be can be implemented for these 2 kinds of activation routes with physical, uses temperature as well as chemical to be combined to make a shorter as well as to make a higher effective activated carbon. So I think I skip this one, and maybe shortly here the kind of electrodes, the electrolytes, even different electrolyte and also different concentration. The voltage used implemented when the capacitor or electrode has been tested, and here specific capacitance of in farad per grams, and here the retention or cycle life of the supercapacitor. As we have seen in our previous slides, that supercapacitor can be run to 20,000 cycles, like here, that only reduce only 8% reduced from the previous one. Okay, this is very good, but maybe this is not good for the economic one. Why? When you have very good retention, so people only buy only once, so it's not good for economic. Yeah. Okay, I can skip this one. Carbon super. I encourage you, or we are should be use the bio-based material to be more effective in our daily life. Let's say for the active material of a carbon supercapacitor base. Here, now the comparison various bio-based derived from active carbon as the electrode materials. Many sources here, from coconut to mangoes or orange, the activated method, surface area, and specific capacitance, and this retention of cycle stability. Okay, let's go. This is line projection. I will not tell you here because we do not use this as in our production line, because we just skip here. We use in our group only in our labs, not line projection as an industrial. Here, what we use here in our group, we can produce coin cell supercapacitor as well as now will soon ready in a weeks to be to produce cylindrical types of supercapacitors in our campus. Cylindrical as well as coin cell supercapacitor. Actually, in our daily in our common laboratory equipment, actually we have had it. Yeah, like and magnetic power glass and oven, or maybe magnetic stirrers, you have it. But maybe the daughter plate you can replace with any other kinds of deposition mechanism, like screen printing or any other deposition type. But of course, when you have use here, you can control the thickness of the daughter plate, and the slurry can be very smooth. And maybe you need the press for the coin cell. If you don't have this one, you can use only your electrodes, yeah, the prototype, not the coin cell.
Maybe I will give 1 minute left.
Okay, thank you. One time, thanks. Okay, let's move fastly. This is the materials we have used in our labs. Okay, this is in the table form, and here the procedures. Maybe you can learn and read for the next session. Here the procedures, and here the characterization you have used actually in our labs, in lab of Pak Nana. Here we have this one, and we have this for charge discharge performance. Okay, this is a retention of our materials. Maybe I cannot go further for the specific example of our product. This is the profile of our product. I will skip it. Okay, we go to the last slide, Pak Nandan. Here we are our current project today. We would like to produce this compact supercapacitor to replace or to accompany the battery in our daily life, let's say for motorcycles or maybe for the road lighting, yeah, like in our picture here, for lighting in the road, maybe for lighthouse in the sea, because here we need not only a very long beam, but sometimes we need a very high voltage and high energy or high power beam. So actually we need the supercapacitor, not only battery, also for to be combination with the solar cell purpose. Thank you very much, Pak Nandan. This is our team with the Dian Sigma Global and Yota Aksarangki. This is our entertainment business group. Thank you, Pak Nandan.
Okay, thank you very much. Very interesting talk. Okay. There is one question in the chat room, so I will ask this from Najib. So first is he asking about how to improve the out of the supercapacitor to be in electric vehicle. That is maybe the question.
Well, sorry, can you repeat, Pak Nandan?
How to improve the supercapacitor in order to be used in the electrical vehicle?
Oh, yeah. As I mentioned in previous my slides here, even Tesla now, Tesla, previously they use fully battery, but now Tesla would like to already implemented a combination between supercapacitor as well as battery in the cars of now in a new type of Tesla. But Tesla now implement in two different devices, means around quarter parts of the battery is supercapacitors, and the other 75% is battery. What is the consequence? The consequence is the charging is now shorter, and the car is now having a very high acceleration. They can use to be a reason. Oh, okay. Now back to the question. What we have to do to increase the energy density, because the power density is already very high compared to the battery. So now people run to verify to choose different kinds of materials with very thin, like a graphene, only thin as 1 atom. So in the same size, we expect when we use graphene as a sheet in one sheet, and we can make it series or parallel, we can increase the energy capacity. The power is no question for the supercapacitor, only energy density. The other kind is we can use a combination between the battery type and the asymmetric of supercapacitors, what we call it supercapacity. Actually, the mechanism is in a mix of the supercapacitor and battery. So maybe this is to be a good future of our battery in our daily term, but it's actually supercapacitor mechanism. Thank you, Pak Nanda.
Okay, thank you very much. It's due to the limited time, so we cannot give you more asking. Thank you very much for Professor Markus Diantoro. It's very interesting topic. Now maybe you can close the slide, and now it's time to giving a certificate here. So please. smile. Okay, thank you. Once again, thank you, Prof. Maspur, for very nice research. Also, thanks for the audience. Now, I'm already finishing this session, so I will give times to the host. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Professor Dr. Markus Diantoro. It's very wonderful presentation, and thank you for Associate Professor Nanda Mufti.